In this video lecture, we will look at how to estimate the principal eigenvectors of a dataset, both from scratch and using scikit-learn. Please continue to follow the first notebook, 5.1. The goal of PCA is to rotate the data onto a new basis which represents the axes of greatest variation in the data. For example, I believe you've already seen our dataset which pairs brain volumes of babies with their gestational age at scan. These two variables are clearly highly correlated, which means that knowledge of one gives us all the information we need, subject to a certain amount of measurement noise to predict the other. This makes consideration of both these features in our dataset redundant. We could easily remove one and not lose any predictive power. This property will be reflected by the fact that our data matrix will be singular or rank deficient. PCA is therefore asking the question of whether data would be better represented by a single feature U1 which combines these two features into a new rotated basis. The goal of PCA, therefore, is to find the axes which summarize the variance properties of the data, and through this represent data in a new and reduced set of coordinate vectors in which our features will be uncorrelated. This new basis U is estimated through eigendecomposition of the data covariance matrix. So therefore, what we need to know first is how to calculate the data covariance matrix. We all hopefully know that to calculate the variance of some vector, we must estimate the sum of squared distances between all examples and the sample mean. We then normalize by dividing through by n-1, where n is the number of examples, to obtain the sample variance. The covariance of two different vectors is instead a measure of the joint variation or covariation of two random variables, x and y. It's related to correlation, where actually correlation is a normalized form of covariance. We can therefore make estimates of variance or covariance for all feature dimensions in order to obtain a covariance matrix. For example, assuming that we have two features, our data is two-dimensional, we can return a 2x2 covariance matrix with variances on the diagonal and covariances on the off-diagonal. The key idea of PCA, therefore, is that we want to find a new basis U for which the spread of the data is maximised. So, rather than using the coordinate bases x and y, we want an intermediate direction U over which the data varies fastest. In other words, we're looking for a direction U1, which, when we project data onto it and subsequently estimate the variance along that sole direction, it will return the biggest estimate of variance that we can achieve as compared to any other possible direction through the feature space that we choose. This can be seen here, where the spread of data points projected onto the eigenvector U1, so where the original points are blue and the projected points are red, has a larger spread than if the points were presented on the x or y directions. Remember that to project any vector x onto another vector u, we need to use the dot product, as shown here, where this estimates the element-wise multiplication and sum of these two vectors. This allows us to find the direction u by optimizing or maximizing our estimation of the covariance with respect to u. To achieve this, we first need an expression of the variance of the data after projection. Thus, if S here is our full m by m covariance matrix, where importantly xn here is a vector of values for all features for each sample n, and therefore x bar is also a vector of length m, where m here is the number of features, then we're able to estimate the covariance following projection onto U1 using the dot product projection as shown on the previous slide. This is applied to the vector itself and to the sample mean. Then, to estimate U1, we seek to maximize the projected variance with respect to U1. This can be achieved by taking the derivative of this operation with respect to U1, while simultaneously setting constraints to prevent the magnitude of U blowing up. Specifically, we constrain U to have unit magnitude. You may have learned through your lectures on support vector machines or through previous classes that constrained optimization can be achieved through the method of Lagrangian multipliers. So this just means that we add in the constraint term here, regularized by the parameter lambda1. So this bit in brackets here just summarizes the term that should be constrained as close to 0 as possible. Then when we take the derivative of this expression with respect to U1, it will return SU1 equals lambda U1, the familiar eigenvector equation. This means that U1 must be an eigenvector of the covariance matrix S. And if we reorder this equation by pre-multiplying through by U1 transpose, which will remove U1 from the right-hand side, since U1 transpose U is equal to 1, this gives us our expression for the projected variance from the previous slide, and thus the first eigenvector represents the direction of maximal variance, and the eigenvalue lambda 1 returns the magnitude of the variance in that direction. We can then repeat this process to extend to higher dimensions. So our next choice of eigenvector is constrained by the assumption that the basis is orthogonal, and thus represents a rotation and projection of the coordinate space. Thus now, when we seek our second eigenvector u2, we instead have two Lagrange multipliers, lambda 2 and phi, where lambda 2 constrains the second eigenvector to unit magnitude, and phi sets the projection of u2 onto u1 equal to 0. So this is constrained to be 0, and this is constrained to be 0. Then, when you take the derivative with respect to u2, we get the following equation, which, if we left multiply through by u1, shows us that phi must be 0 as the covariance and the projection of u1 onto u2 are constrained to be 0 because they're orthogonal. And if this disappears, we are then left again with the eigenvector equation, this time for u2. Accordingly, this derivation leads us to our first method for estimating our PCA eigenvectors through eigendecomposition of the data covariance matrix, where here we're writing our expression for the covariance matrix more compactly by assuming that our data matrix has been demeaned. Please remember that this will involve subtraction of the mean vector length m, summarising mean values for each feature from our data matrix X. We can then perform standard eigenvector decomposition. This we demonstrated in the previous video for 2x2 matrices, but now at high dimensions we're expecting you to perform this using NumPy. This will then return an orthogonal matrix of eigenvectors U and diagonal matrix lambda, which contains the eigenvalues. Note, the specific dimensions of S and therefore U will depend on whether you are exploring variance across samples or features, and thus whether you have calculated S from X transpose X or XX transpose. These eigenvectors represent the principal components, orthogonal directions of maximal variance, where eigenvalues represent the proportion of data variance explained by each. It's common practice to reorder our set of eigenvalues and vectors by eigenvalue magnitude, starting with the largest, so as to represent the new coordinate basis in descending order of explained variance. We are then able to project all of our data onto this new rotated basis using U transpose X. Thus, in summary, and you will be asked to implement this in Tuesday's tutorial, the steps to estimate the principal components from the eigenvectors of the data covariance matrix are as follows. First, demean the data by subtracting the mean vector x bar. Here, x and x bar are column vectors. You can do this using NumPy mean, but remember to specify that you want to return the mean over columns and not the mean over all elements. So this is going to require you to supply the axis argument. Next, use NumPy's function for eigenvector decomposition to return a matrix of eigenvectors and one of values. This is the NumPy function .eig. It returns unit eigenvectors, but it doesn't sort them, and sorting will be essential for later when we seek to reduce the dimensionality of our data by projecting onto this new basis. Estimation of the eigenvectors of the data covariance matrix works fine provided your covariance matrix is full rank, estimated on the smaller of your data matrix dimensions. However, when it's not, it can be unstable. It's therefore more common practice to estimate PCA using singular value decomposition, or SVD. So SVD supports eigendecomposition of non-square matrices expressed in the following way. This factorizes data matrix X into three matrices, where U are the left singular vectors. These are orthogonal, so U transpose U is equal to the identity. Lambda here represents a rectangular diagonal matrix of singular values. I will show you what this looks like on a later slide. However, the most important things to note are that these are related to the eigenvalues of the data covariance matrix in the following way, and that the number of singular values is determined by the matrix rank, where the rank will be equal to the minimum of the dimension, so either M or N, M in the example that we're giving here. Finally, V are the right singular vectors, which are also orthogonal, and U and V have unit size, so they don't need to be normalized. Then, to implement this in NumPy, what you need to do is first subtract the mean vector, as before, and then estimate the singular vectors and values of the data matrix X using NumPy's SVD function. Noting that to project data onto this basis so as to maximize variance between samples, you want to project onto the matrix U. Note, NumPy SVD returns eigenvalues and vectors ordered by size, so you don't have to do this yourself. And the right singular vectors will be transposed by default. So in other words, V returned here is equivalent to V transpose from the equation on the previous slide. Some of you may be wondering how SVD links to PCA and the estimation of eigenvectors of the data covariance matrix. So by way of explanation, we can see this by creating covariance matrices X, X transpose, and X transpose X. And then we can substitute the SVD decomposition for X into these. This returns that X, X transpose is equal to U times lambda squared times U transpose, and likewise for V. It is then possible to show that in the case that n is greater than m, these two covariance matrices will share m eigenvalues and the rest will be 0. This is because when you estimate the eigendecomposition of X, X transpose, this will return for a single eigenvector U and corresponding singular value sigma squared the following familiar eigenvector equation. We can then see that if we pre-multiply by X transpose, that sigma squared is also an eigenvalue for the covariance matrix X transpose X with eigenvector V equals XU. Thus, both of these covariance matrices share M eigenvalues, and as X is a non-square matrix and thus has rank equal to the smallest dimension, in this case M, the M by N covariance matrix will also be rank deficient. This means that there are most M non-zero singular values indicated by the fact that the lambda matrix of eigenvalues has rectangular diagonal form, as shown here. To best understand how PCA works and the importance of considering how the operation should be implemented with respect to the dimensions of your matrix, we will ask you to calculate PCA from scratch using SVD and the covariance matrix during the Tuesday tutorial. However, going forward, I expect that you will use the scikit-learn implementation. You should now be familiar with the scikit-learn API. This here is the constructor. To call it, you need to import PCA from the scikit-learn decomposition module, then initialize it with a choice of arguments, including, for example, how many components you want to return, and then you fit in the normal way. Noting that, as with all scikit-learn modules, it will be expecting the data to be supplied with examples on the rows and features on the columns. So this is the transposed orientation to the convention that we've used thus far. Once fit, the PCA class has a number of attributes that it can return, including the components, the explained variance, or the lambdas, the singular values, or their sigmas, and the data mean. And finally, a note about what PCA is very commonly used for. So PCA is a very common pre-processing step to many image processing or data pre-processing tasks. It supports data whitening or decorrelation, as we will see later in the ICA lecture. However, most commonly, it's used for the task of dimensionality reduction, which is projection of the data onto a reduced linear subspace with few coordinates. We know that through SVD, the data is automatically reduced to at most m eigenvector eigenvalue pairs for n is greater than m, as this corresponds to the matrix rank. However, further reductions in dimensionality can be achieved by selecting the eigenvectors corresponding to the k largest eigenvalues, where k is less than m. This has many benefits relating to reducing overfitting, and it can also be used for denoising, as many components with very small lambdas can be considered as just noise. This is the reason why we want your eigenvector eigenvalue pairs to be ordered, as what you want to do is return or choose just those eigenvectors which correspond to eigenvalues with high variance. To choose how many and which eigenvector eigenvalue pairs you want to keep, what I recommend you do is look at the cumulative distribution of the eigenvalues and then select a cutoff at the point where the curve flattens off, or, for example, by selecting all components which sum to a specific proportion of the data variance, for example, 90%. And very finally, linking PCA back to the concept of linear transformations or rotations, this slide shows that the operation of the covariance matrix S on uncorrelated Gaussian noise is to scale and rotate that data into a new coordinate basis, similarly to the example seen in the last video. So, in summary, the goal of PCA has been to rotate data into a new basis which better represents the variance of the data. It's achieved through estimation of the eigenvectors of the data covariance matrix, where we're interested only in the eigenvectors corresponding to non-zero eigenvalues, noting that for ranked efficient matrices, it's much more stable to calculate this using SVD or singular value decomposition. This automatically reduces the data dimension to the rank of the data matrix. However, further dimensionality reduction may be achieved by ranking eigenvalues and therefore their associated eigenvectors by order of size, largest to smallest, and then keeping only the eigenvalue eigenvector pairs which sum to a specific percentage of variance for the data. And finally, to understand what is happening, it can help to see PCA as learning a basis which diagonalizes the data covariance matrix, and this generates a rotated coordinate basis which more faithfully represents the variance distribution of the data. So that's it for PCA. Please attempt the Keats quiz before moving on to the next section.